Hello and welcome back, everyone. In the last few playtime videos, we have performed data aggregation, as well as a few data pre-processing steps like outlier detection and removal and missing data imputation on our electricity demand prediction dataset. Now that we have a better understanding of what data normalization is and why it is necessary, let's go ahead and perform these on our dataset. For this project, we will implement two normalization techniques, the log scaling and the z-scaling. Log scaling, as we discussed in the previous video, is usually performed on features that have values that scale, like the price of a house or the loan amount issued by banks to applicants. Z-scaling, on the other hand, is more common and used for most numerical features, and while we will be demonstrating both, Z-scaling is the one we will move forward with for this project. With that said, let's start with the first implementation, which is log scaling, by taking a quick look at our dataset. As can be seen, our dataset has 9 features, with temperature values in degrees Celsius and humidity values between 0 and 1. To implement log scaling, we first create a list of continuous value features that we would like to scale, which in our case is temperature, feel like, and humidity. Next, for each of the data points in each of the columns, we simply perform a base 10 log on the value using the math library's log10 function. As before, to speed up the code, we use lambda function instead of loops for going over all the data points in a column. Also, as before, since the train and test features need to be in the same form, we perform this operation for both the train and the test set and use the describe function to display the data after this operation. If you run this cell now, you will notice that the values for our 3 columns have been modified. Nice. Okay, let's now see how to implement z-scaling. The code, as you can see, is not that different from log scaling. Like before, we start by creating a list of continuous value features that we would like to modify. Next, we calculate the mean and the standard deviation for each of the features. And finally, for each data point in a column, we subtract the mean from the value and divide the result by the standard deviation. If you run this cell now, you will notice that the means of all the 3 columns are extremely small values close to 0, and the standard deviation is 1. Mission accomplished? And that is all for this video. In the next video, we will explore another data pre-processing step, namely the data binning or bucketing. So, see you there.